this preprint here with Jonas Schnitzer. And well, it's basically just the observation that twisted L-infinity morphisms are in some nice settings homotopic, and that we can apply this to the globalization of the Kontsevich formality and look at its homotopy classes here. So the outline of my talk is like this. First, I want to give you some basic ideas about deformation quantization and what the Kontsevich formality theorem states, and a bit how the globalization works. Then we need to recall some notions, so Maurer-Cartan elements and equivalences between them and the twisting procedure. Then in the third point, I want to tell you what homotopic L-infinity morphisms are and prove this theorem that the twisted morphisms are in some cases homotopic. And then we will apply it to the globalization. So the first, deformation quantization, the setting. So from the classical point of view, like motivated by classical mechanics, one is interested in Poisson manifolds, which are kind of the phase space of the system. And well, the smooth functions are then the observable algebra. And we have here the pointwise product and of course the Poisson bracket, which encodes the time evolution in Hamiltonian mechanics. And as you all know, this Poisson structure here is a Maurer-Cartan element in the DGLA of polyvector fields. So zero differential and Schouten bracket here. And the whole idea of deformation quantization, or of formal deformation quantization, is that one wants to get the quantum observable algebra as a formal deformation of this classical one. So the structure one is interested in is this star product, which is a bidifferential associative product on the formal power series of functions here, where h bar is just some formal parameter. And it should deform the classical structures. So the star product is in lowest order of h bar, it's just the pointwise product plus some higher order deformations. And the commutator of the star product vanishes in zeroth order because the pointwise product is commutative, and in first order of h bar, it should be just the Poisson bracket, and then again, plus some higher order deformations. And one can check that these higher orders of the star product, so all the terms depending on h bar, are a Maurer-Cartan element in the DGLA of polydifferential operators. So this here are formal power series in h bar of differential Hochschild cochains. This is just the Hochschild differential, and the bracket here is the Gerstenhaber bracket. So sometimes I will omit the bracket in this list. So vector space, differential, and bracket, and sometimes I don't write a bracket. So, well, deformation quantization is then about the existence of star product. So thus for every Poisson bracket, does there exist such a star product deforming it, and how many exist? And this is answered by the formality theorem here. So it states that there exists an L-infinity quasi-isomorphism between the formal power series of vector fields, so just taking here formal power series in h bar, into these differential operators, and that it induces a bijection between the equivalence classes here of formal Poisson structures and the equivalence classes of star products. And okay, formal Poisson structure is just a formal power series of bivector fields that commutes with itself. So like a Poisson structure, but formal power series. And well, this answers the problem. So for each Poisson structure, this formality allows to construct a star product deforming it. And for each star product, it associates some equivalence class of Poisson structures. So it shows existence and classification of star products. And well, Kontsevich actually proved this only for RD, and the globalization to general manifolds was done by Dolgushev. So let me give you a very basic idea how this works. So on the one hand side, we have like vector fields with zero differential and Schouten bracket, and here differential operators with Hochschild differential and Gerstenhaber bracket. And the first step is to construct these Fedosov resolutions here. So differential forms in M with values in the formal fiberwise polyvector fields and formal fiberwise polydifferential operators. One has here then the fiberwise Schouten bracket and here the fiberwise Gerstenhaber bracket. And one has as differentials the Fedosov differential here, and on the side of different differential operators, the Fedosov differential plus the fiberwise Hochschild differential. And these maps taus here are Taylor expansions, and they are quasi-isomorphisms of DGLAs. And well, the point is that this Fedosov differential here can locally be written as the de Rham differential plus a bracket with some element B. And this element B depends on the choice of a covariant derivative on M. And well, the bracket is here the Schouten bracket, in this case it's the Gerstenhauer bracket. And so for this globalization of the formality, it somehow is enough to relate these Fedosov resolutions. And there one can show that one has some fiber-wise Kontsevich formality here. And to make it compatible with the Fedosov differentials, one has to twist it by this element B. So if I have time, I will give you more details on this later. So just believe me that the Kontsevich formality is some quasi-isomorphism between them, L infinity quasi-isomorphism. And then in the next step, one can construct the L infinity quasi-inverse of this tau here. And since one has here a homotopy for this differential, there are explicit formulas for this. So this P is easy to understand. And the globalized formality is then just Taylor expansion, then fiber-wise formality, and then projecting downstairs. Okay, and well,
can I ask what
sure.
B is again?
P? Sorry?
Can you say
this,
again what B is?
This B here?
Yeah.
This is like the Christoffel symbols of the connection plus some correction terms to make it flat.
But so it's an object that just depends on the connection.
Yes, exactly.
Okay.
And well, it's only locally defined because the Christoffel symbols are not don't conform as tensor fields. Okay. So there's also a different description which is globally well defined, but I didn't want to put it here. And okay, so this depends on some connection. And there's this observation that changing the connection is the same as twisting this differential with a Maurer-Cartan element equivalent to 0. And this will allow us to show that the globalized formalities are homotopic. So if we do just the same for a different connection, we will get something homotopic. Okay, so this is the plan. Let's start with the basic definitions. So, well, a DGL8 differential graded Lie algebra over some field of characteristic 0 is just some set graded vector space with a graded Lie bracket. So it's graded antisymmetric and graded Jacobi identity and some differential of degree +1, square to 0, and Leibniz identity. And a Maurer-Cartan element in here is an element of degree 1, satisfying this Maurer-Cartan equation. So if the differential is 0, like for vector fields, this is just an element that commutes with itself. So Poisson structure in this case. And nice thing is that we can twist with Maurer-Cartan elements. So this equation here basically ensures that D plus the bracket with pi is again a differential, which is then called twisted differential. And we already saw one example in the last slide. This Fedosov differential was like de Rham plus bracket with B. So it was de Rham differential twisted with this B. Okay, so now a notion of equivalences between Maurer-Cartan elements. So taking two of them, we call them gauge equivalent if they are related by this expression here, where G is an element of degree 0. And well, since we have some infinite series here, we will assume always that we have complete descending filtration and that the pi's and the g's are in the first order of the filtration, and then this is well defined by the completeness. Okay, so the explicit formula is not really important. It's just that if pi is a Maurer-Cartan element, then this one is again a Maurer-Cartan element. And the set of equivalence classes is denoted by def for deformations. So maybe let's look at an example. I mean, in the formality theorem, we had on one side the formal power series of vector fields. So let's look at this. And nice thing is that this formal power series here induce such a complete descending filtration just by taking here the orders in H bar. So an element in degree 1 and filtration order 1 is just some formal power series of bi-vector fields starting in H bar, and an element of degree 0 with filtration order 1 is just a formal power series of vector fields now starting in H bar. And well, for this gauge action, we have no differential, so this term does not contribute. And bracket with a vector field is just the Lie derivative. So in this case, the gauge action is just the action by such a formality theomorphism. So it really makes sense, and it's what we want in our setting. And another nice consequence of this gauge equivalence is this. So we saw that we can twist the DGLAs with Markov-Cartan elements, and the point is that if we twist them with equivalent ones, that the twisted structures are isomorphic just by this element here, which implements the gauge equivalence. So this will be used later on. Okay, so this was the setting of DGLAs, and now we do just the same for L-infinity algebras. So please interrupt me if you want more details on something. I will just give the basic definitions of all this stuff. So an L-infinity algebra structure on some vector space is a degree 1 codifferential on this co-commutative coalgebra. So this is just the reduced symmetric tensor product, so without the field, only symmetric degrees greater than 0. And this is the shuffle coproduct on it. And since the symmetric tensor product or symmetric coalgebra is co-generated by L, this codifferential is determined by its projection on L. So by such maps, such a sequence of maps, they are called structure maps of Q. And well, since L is of since Q is of degree 1, it maps here into L shifted by 2. And the fact that it's a codifferential, so that it squares to 0, leads here to some equations for these structure maps. So by these indices here of the maps, I always indicate on which symmetric orders they live. So this maps from symmetric degree n to symmetric degree 1, and so on. And well, the example we are interested in, so in the information quantization, we will only consider DGLAs, never L-infinity algebras. So let's check that DGLAs are really in the setting. And well, this is quite easy. We have just two structure maps. The first one here, the 1, 1, is just the differential with a minus sign. And well, the second one is just the Lie bracket with some weird sign. And the sign comes from this shift here, basically. And the higher brackets are 0. So what does this mean in this case? For n equals 1, we have here just q11, q11 is 0, so that this squares to 0. And well, for n equals 2, this is just the differential and bracket satisfied Leibniz identity. And for the next one, it's just the Jacob identity for the Lie bracket. So if you want, an L-infinity algebra is just like DGLA with higher brackets. And for example, the second bracket satisfies then only Jacobi up to higher brackets, and so on. So we can generalize now Markov-Cartan elements to this L-infinity algebras. We assume again that we have a complete descending filtration. And okay, before Markov-Cartan elements were of degree 1, and now in this shifted space they are of degree 0. And the Markov-Cartan equation becomes this. So with L is just a DGLA, we only have two terms, right? The first one is minus the differential, and next one is minus the bracket. So it's up to a sign, really just the Markov-Cartan equation from before. And again, this series here is well defined because of the filtration. So we can also generalize the notion of equivalence between Markov-Cartan elements, which is now called homotopy equivalents. So two Markov-Cartan elements are homotopy equivalent if we have here such paths pi of t and lambda of t, such that pi evaluated at 0 is the first one, at 1 it's the second Markov-Cartan element, and we have this differential equation. So it's just the higher brackets with 1 lambda and filled with pi's. And this is basically to ensure that pi is a curve of Markov-Cartan elements, so evaluated at each t is a Markov-Cartan element. And these spaces here are like constructed as follows. So we take polynomials in t with values in L, then they inherit the filtration from L, and then we complete with respect to this filtration. So this is just to make sure that the evaluations are well defined. If we would here take like formal power series or something, this might not be well defined. Okay, so now we have this homotopy equivalence, and we had before this gauge equivalence. So let's compare them for DGLAs. The one direction is pretty easy. So if we have two gauge equivalent ones, then we can construct this homotopy equivalence data like this. So lambda of t is just constant g, and the path pi of t is just the gauge action of tg. So for t equals 1, this is pi 1. For t equals 0, it's pi 0, and it satisfies this differential equation from before. So we have one direction going from gauge equivalence to homotopy equivalence, but we also have the other one. This is a theorem by Manetti that says that two Maruka-Tan elements are homotopy equivalent if and only if they are gauge equivalent. And well, to make this more explicit, if we have such a homotopy equivalence data here, one can construct out of this lambda of t another polynomial or another path in this completion a of t, such that pi of t is actually the gauge action of a of t. And then we evaluate at 1 and we get the gauge equivalence. And well, the reason I introduced this homotopy equivalence is because it's much nicer compatible with L-infinity morphisms than the gauge equivalence. So let me give you the definition of L-infinity morphisms. It's just a graded coalgebra. So it's a morphism of graded coalgebras of degree 0 that commutes with the codifferentials here. And again, this is co-generated by L prime. So this is uniquely determined by its projection on L prime, so by such structure maps again. And well, again, this leads to some compatibility conditions between structure maps of F and structure maps of Qs. And I only wrote the lowest one here, which just says that F11 is a chain map here. And then we can define what an L-infinity quasi-isomorphism is. It's just an L-infinity morphism whose first structure map is a quasi-isomorphism of cochain complexes. Okay, now let me collect some properties related to L-infinity morphisms and Maruka-Tan elements. So I wrote this proposition just for DGLAs, but it works just the same for L-infinity algebras. Well, the first observation is that such an L-infinity morphism provides a way to map Maruka-Tan elements in G to Maruka-Tan elements in G prime, just by this series here. And well, this map is even compatible with the equivalences, so it induces a map here on the deformations. And if the L-infinity morphism is a quasi-isomorphism that is in some way compatible with the filtration, then this map here is a bijection. So this is what I told you about the formality by Kontsevich, which induced the bijection between equivalence classes of Poisson structures and equivalence classes of star products. Okay, and we saw that we can twist the DGLAs by Maruka-Tan elements, so we can twist this by pi and this by f of pi, and there exists also some twisted L-infinity morphism. And we saw L-infinity morphisms are determined by its structure maps, so this is also determined by structure maps, and they are quite easily described. They are just the structure maps of F filled with some pi's here. And again, 0 is well defined because of this filtration stuff. And what's nice is that if F is an L-infinity quasi-isomorphism, then the twisted one is also an L-infinity quasi-isomorphism. So like L-infinity morphisms and Maruka-Tan elements are as nicely compatible as you could wish. And well, the one example of L-infinity morphisms we're interested in is the formality. So the theorem is like this: there exists an L-infinity quasi-isomorphism between the Pauli vector fields on Rd into the Pauli differential operators on Rd. And well, its first structure map is just the Hochschild-Constant-Rosenberg map, which is just the anti-symmetrization of the vector fields, which is a quasi-isomorphism. And okay, we will only use this as a black box, but proof is pretty hard, but it has some nice properties. So one property is that we can replace here Rd by its formal completion at the origin. And another property is that the formality is equivalent with respect to linear transformations. And these two properties ensure that we have this fiber-wise Kontsevich formality between the fittest of resolutions. Now at first here with 0 differential and here just with with Hochschild differential. And well, next step, we can go in some coordinate chart where we have the de Rham differential. And since the de Rham differential just acts here on the classical side and the formality just on the formal coordinates, they don't interact, and this is still a quasi-isomorphism here. And then we saw that the Fedosov differential was like d twisted by this element b. So we can just twist this equation. We get here the twisted Kontsevich formality from the Fedosov resolution into the twisted Fedosov resolution. And now here, this is twisted by this element. But again, using the properties of the Kontsevich formality, one can check that this is just B. So here one has really just the Fedosov resolution. And then in the last point, one has to check that this is even globally well defined, not just on these charts. But this works also. And so we have this fiberwise twisted formality we used in the globalization procedure. Okay. And now suppose we are in this setting, again, back in the general case. Suppose we have some L-infinity morphism between two DGLAs. And we have in the first one a Marucatan element which is equivalent to 0. Then we know that our L-infinity morphism maps this to a Marucatan element in G prime, which is again equivalent to 0. And okay, so what I want to mention, this G and this G prime for the gauge equivalences, there's no real obvious connection. So we have to switch here from gauge equivalence to homotopy equivalence. Then we apply our infinity morphism and get an homotopy equivalence in G prime. And then we switch again back to the gauge equivalence by constructing this path A and evaluating at 1. But what we get is some diagram like this. So remember, I told you before, if we twist with equivalent Marucatan elements, we get isomorphic GLAs. So we twist with 0, nothing changes. We twist with pi, and they are isomorphic just by e to the bracket with g. And the same here. So what we can do, we can just take our L-infinity morphism F, or we can twist the DGLA, take the twisted morphism, and twist back. And well, this is in general not the same, but I want to show that it's the same up to homotopy. So let me tell you what I mean by this up to homotopy. And well, the idea is here to interpret L-infinity morphisms as Marucatan elements. And then on these Marucatan elements, we have the homotopy equivalence relation, which we can use to define what homotopy equivalence between L-infinity morphism means. So this is this proposition that says that on this space, we have some L-infinity structure whose Marucatan elements are just L-infinity morphisms. Okay, the underlying space here are linear maps from this symmetric tensor product here into L prime. And this has a complete descending filtration, just given by this symmetric decree here. So we say that a map here is in filtration order K if it vanishes in elements with symmetric degree less than K. So an element of filtration order 1 vanishes on symmetric degree less than 1, but there is nothing. So everything in here is of filtration order 1, and all twisting stuff and all series are all well defined. So we don't have to worry about this. So we only have to give the structure maps of the codifferential. And okay, the first structure map, the 1,1, is just pre and post composition of the map with the differentials on these spaces, like you would do for maps between cochain complexes with some sign in between. And the higher brackets are just constructed convolution-like. So we take here the coproduct on this symmetric algebra to get n factors. Then we can apply our maps and take the symmetric product of them. Then we will end up in the symmetric algebra of L prime. And then we can take here the higher bracket to end up with something just in L. And well, that this is a L-infinity structure is pretty clear because Q prime and Q are L-infinity structures. So this is not hard to show. So let's take a look at its Marucatan elements. Marucatan elements are of degree 1 in this space. So they are maps from the symmetric algebra of L shifted by 1 into L prime shifted by 1, like we saw for L infinity morphism. So the degree fits. And then if it's of degree 1, we have here no sign. And one can check that the Marucatan equation is really just the same as saying Q prime F minus FQ is 0, so that it commutes with the codifferentials. And then we're done. Okay, and well, what's also nice about this is that if L prime here is just a DGLA, so it has only a differential and binary bracket, then this convolution L infinity algebra will also just be a DGLA. So we have, if Q prime has only some binary stuff and no higher brackets, then Q hat will also not have higher brackets. Okay, so we can define two L infinity morphisms are homotopic if its structure maps seen as elements in here are equivalent Marucatan elements. And well, let me give you some properties. So let F and F prime be homotopic L infinity morphisms. Then one can directly see that the 1-1 components of these L infinity morphisms are chain homotopic in the classical sense. So if F is an L infinity quasi-isomorphism, then the other one is 2. And well, the proof, or the idea of the proof is pretty simple. So remember that homotopy equivalence means that we have such a path f of t and a path lambda of t that satisfy this differential equation, and such that f evaluated at 0 is the first one, and at 1 it's the other L infinity morphism. So if we look here at this equation and just at the 1-1 component here, then on the right-hand side we get only Q prime 1-1 with lambda 1-1 and the other way around. Then we can integrate this equation and we directly get their chain homotopic. Okay, and well, the third point here is also pretty nice. It says that homotopic L infinity morphisms induce the same maps on the deformations. So for this, we have to show that taking some L infinity, taking some Marucatan element in L, that F and F prime map this one to equivalent ones in L prime. And basically, with this equation, one can directly construct the homotopy equivalence between the images. And then the last 2 points are not really surprising. So pre and post composition of homotopic L infinity morphisms with an L infinity morphism are again homotopic, as you would expect. Okay, so let us now consider this setting from before. Like we consider twisted morphism and twist back, or we take just our morphism. And the statement is that both are homotopic. So this means they are homotopy equivalent in this DGLA. So we need some path between F and this twisted one, and some path lambda of t such that they satisfy this differential equation. And just the idea, so the path between F and between this one is pretty easy. So we just write everyone here at t dependency. Evaluating at 1, it's just this one, and 0, it's just F, because pi at 0 vanishes, a at 0 is 0, and a prime at 0 is also 0. So this is a path between F and this twisted one. And then one can check setting lambda bullet of t, so this path of maps in here, like this, that they satisfy this differential equation. And well, it's just some lengthy combinatorial computation. It's not really hard. It also somehow makes sense. I mean, this path lambda of t is just the same as this f, just that we add here one lambda of t, where this lambda now is from the homotopy equivalence between pi and 0 in G. So, okay, the notation is probably a bit bad here. Sorry. But well, this shows that this diagram here commutes up to homotopy. And yeah, let's use this now for the globalization of the Kontsevich formality. So remember, we had the globalization worked like this. We had Taylor expansion fiberwise twisted formality and then projecting downstairs with this Fedosov differential. And well, we take now some second covariant derivative, then we get some tau prime, some p prime, and also a prime p prime here, which is Theram plus b prime. And well, these two are only defined locally, as I said, because they depend on the Christoffel symbols of the connections. But the difference between the connections is a tensor field, so the difference between b prime and b will also be globally well defined. So it's the one form with values in the fiberwise vector field. And there's this observation by Pushkin, Dolgushev, and Waldman that this difference b prime minus b is gauge equivalent to 0 in the Fedosov resolution here. So there exists some element h such that b prime minus b is the gauge action of h on 0. And I didn't tell you, but one can check that one has on these Fedosov resolutions here some complete descending filtration, which is basically just given by the form decrease and here the formal decrease. And okay, so we have here two equivalent Mahokan elements, so the twisted structures will be isomorphic. So twisting by 0 doesn't change anything. And if we twist d by b prime minus b, we get just d prime. So this just says that the two Fedosov resolutions are isomorphic as the GLAs, which is also not really surprising. But well, so let's summarize in this diagram. We have the polyvector fields in M. We can take Taylor expansions with respect to one connection and end up in this Fedosov resolution, or we take the one with respect to a different connection, end up here, and they are isomorphic by the last corollary. Then we have here the twisted fiberwise formality with one connection and with the other connection and the two projections. And the point is that here the Fedosov resolutions are again isomorphic and even by the same element h. So in general, one would have here different, one could have here a different element, but again, by the properties of the formality, this is just the same. And then, okay, so going downstairs is just twisting by b prime minus b. But the formality twisted by b prime is also just the formality above twisted with b prime minus b. And this is just twisting back. So this central square here is just this general diagram I had before. And there we showed that this commutes up to homotopy. So the fiberwise formality twisted by b is homotopic to this composition. And well, then one can check that this triangle here commutes even directly, and that this triangle commutes up to homotopy. But well, then the whole diagram commutes up to homotopy, and the one globalized formality is homotopic to the other one, which is just the way downstairs. So summarizing, we've shown that if we take two covariant derivatives, they should be torsion-free, then the globalized formalities are homotopic. And in the case that one has some Lie group action, and one chooses G-invariant covariant derivatives, then the formalities will be equivalent, and also the homotopy halves between them are equivalent. So this whole construction is nicely compatible with group actions. And one consequence of this is that the map on the level of deformations does not depend on the covariant derivative. So remember, we had this general statement that homotopic L-infinity morphisms induce the same maps. Sorry, G is some Lie group. So this in brackets here is just for the case that we have some Lie group action on the manifold. Okay, and well, this statement that the map on the deformations does not depend on the covariant derivative was also shown by Pushkin, Dolgushev, Waldman, but they constructed like explicitly an equivalence of the star products. And we get it like for free because we consider this whole stuff at the level of the formalities, not at the level of Mahokan elements. And what I also want to mention is that this construction is like functorial. So the association from manifold M to the homotopy class of L-infinity morphism between T-poly and D-poly is a functor if we start here in the category of manifolds with diffeomorphisms. And well, this is what I call homotopy arrow category. I don't know if this is the real name. What I mean is just that the objects in here are homotopy classes of L-infinity morphisms. And the morphisms here are like homotopy classes of morphisms such that the diagram commutes like for the arrow category, but with homotopy classes. Okay, and here are some references I used, and that's it. So thank you for your attention.